Nice. Okay. Let me uh, introduce myself. I am Aniket. I recently joined NEC Labs America, and I recently graduated from Johns Hopkins with Professor Rama Chilappa. And it's a great honor to present my work here. So the work I'm presenting today is like a recent advancements in image generation and understanding. So let's begin. So over the overview of the talk is I'll be explaining the introduction, then one of my recent work called DiffNat, which published in TMLR, and some future directions, and followed by some question and answers. So first of all, so let me start with the evolution of image generation. So as you all know that image generations is improving like very fast these days. Before 2014 onwards, before that, it was generally Gaussian mixture model or very some kind of handcrafted model where the imagination qualities are not that great. For example, here you can see the MNIST generation results are not that great. But 2013 to 14, here comes new models called variational autoencoder, which improve the image quality, but not that great. 2014 onwards came generative adversarial networks or GANs, which improve the quality quite a bit. For example, you can see the face generations are pretty good and pretty nice compared to what was there earlier. But 2020 onwards, here comes diffusion model, which improve the image quality quite significantly. The clarity, resolution, and the realism you can see from these image generations are pretty realistic. And that's how the image generation quality these days, image or video generation qualities has progressed a lot. And a bit of background of what diffusion models are. So diffusion model, what it does is it's an iterative denoising method. So for example, you start with a real image called X0, and you add noise to the image iteratively till it becomes totally random noise like XT. And the goal is from the noisy version of the image, how you can denoise to generate to reconstruct the original image. That was the goal to uh, for the diffusion model. So that's why it called the denoising objective, that you have to iteratively denoise the images till it becomes realistic image. Yeah. In this context, we present our work called DiffNat, that improving diffusion image quality using natural image statistics. This, as I mentioned, published in TMLR recently, is joint work with Maitreya, Anshul, Ketul, Jiang, and Professor Chilappa. So the goal of this work is to improve the image quality. And the challenge is that I already mentioned that you have seen different new kind of models coming in, right? For example, earlier there was GMM, then VAEs, then GANs, and then diffusion models. But we thought, can we do something very generic and won't be like conditions on the model? So it should not be dependent on the model. So is that any way we can improve the image quality in a universal way? To this end, basically, we propose this the DiffNet work, where the key novelties in this work is that, first of all, we use the kurtosis concentration property of natural image as prior. And based on this prior, basically, we propose a plug and play kurtosis concentration loss. And we also propose a perceptual guidance strategy. Uh, yeah. So first of all, am I audible?
You are audible.
Okay, cool. Got some kind of a message, that's why. Um, okay. Yeah. So as I mentioned, that three novelties in this work, this kurtosis concentration property as natural image prior, propose a plug and play kurtosis concentration loss, and also a perceptual guidance strategy. Now, what is the kurtosis concentration property of natural images? It sounds interesting, but what is it? Let me explain that. So it is a known property of natural images, which was proposed earlier, like classical works. And what it says that if you have a natural image like this, and you perform discrete weather transform across multiple filter banks, which will generate different filtered version of the image. If you compute the kurtosis, and kurtosis is basically the fourth order moment of fourth order moment as shown here. The kurtosis values across those filtered version of the images seems to be constant to some specific value. That property is called kurtosis concentration property. This property has been used earlier for detecting real versus synthetic images because real image or natural image has this property, but synthetic image or generated image don't have this property. So based on the fact that this is a prior of natural image, uh, this property or this kind of prior has been used to identify if an image is real or fake. But here we try to use in a different way, as I mentioned. Yeah. Also, a bit understanding of why this property holds. So it looks interesting, but why this property hold mathematically? So just give you a brief idea of why this property hold. So it has been already known that the distribution of discrete weather transform filtered version of natural image follows a generalized Gaussian density function of this form, where P of XYZ is the probability and X is the random variable and alpha beta are some scaling parameters. So if you compute the kurtosis, which I mentioned, that is a fourth order moment, it actually boils down to a very analytic form, which you can notice that is independent of X. So it is just dependent on the beta values, and the gamma function of the beta values is also some constant with respect to natural images, which has been also empirically proven. So that actually gives the idea why this property holds. And this is a just mathematical understanding of why this property hold, which is kind of uh, give us also intuition for this property. So based on this property, that kurtosis concentration of natural images, we propose a plug and play loss function. And by plug and play, I mean it can be applied to any kind of generation pipeline, like diffusion pipeline or any other pipeline, and it can improve the image quality even further. So for example, Dream Booth is a very popular image generation pipeline where the goal is to generate different variation of the image, of the specific image from fewer examples. And when we add this kurtosis concentration loss on the Dream Booth setup, we notice that the image quality improves and also the kurtosis span that also reduces. So this actually give a proof of concept of both the ideas and our loss function. So next I'm going to present how the kurtosis concentration loss is exactly applied to any kind of generation pipeline. So suppose if you have some input images, and based on your task, there could be some additional input. It could be images, it could be text, it could be a combination of both, or it could be none. Now, the task in hand, what we are kind of considering was text to image to image generation, and unconditional image generation. And for each of the tasks, there could be different method. Like for example, text to image generation could be Dreamboot style or custom diffusion style. Those are different kind of method for the task text to image generation. Similarly, for image to image generation, there could be different kind of pipelines. It could be Chi diffusion, it could be K diffusion. And for unconditional image generation, it could be DDPM, DDIM, this kind of methods. So now I'm going to explain how this method is applied to the any kind of pipeline. So for example, if I choose Dream Booth here for the text to image generation, so the Dream Booth pipeline might have some task specific additional loss. Like we call is the approach specific task loss. It could be just particular for the Dream Booth pipeline. We are not touching that pipeline or that loss at all. So as I mentioned earlier, the goal of diffusion model is to add noise to the input images and gradually denoise till it get the reconstructed images as close as the real images. So that's why it called the reconstruction objective, that minimize the reconstruction loss. It also terms as diffusion loss as in the literature. So our loss is applied on the reconstruction images. Sorry, reconstructed images. So when you perform the reconstruction objective in during denoising, uh, we kind of in the reconstructed images we pass through the different discrete wavelet transform filtered version of the images, and we simply minimize the maximum and the minimum value deviation of the kurtosis span. Since I already mentioned the goal or the natural prior of diffusion was that across uh, different filtered version of the images, the kurtosis span should be minimized or should be constant. So therefore, the gap should be less. So that's why we are minimizing the kurtosis span, which enforce that your generated images look more natural. So this is a simple kurtosis loss, which could be, and as you can see that the simplicity of the loss function enable it to apply any kind of generation pipeline. So yeah, so this is the kurtosis concentration loss. Next, yeah, then we became more greedy. So like, okay, we can improve the image quality using the kurtosis loss, but we thought, can we improve the image quality even further? And here, this is a training-based method, like this loss function is added to the training pipeline. But we thought, can we do something inference trick, which should be like, which improve the image quality like free of cost? So we can do that. For that we propose the perceptual guidance strategy, which I'm gonna explain next. So in diffusion-based pipeline, the classifier fee guidance is pretty well known or pretty common to improve the image quality as a inference strategy. So what it does, suppose if you have to generate a image with the prompt alien in the beach. Here alien is the condition. So how you can make sure your generation quality is aligned with the condition like the alien. So it starts with the unconditional score, like it costs epsilon theta of xt or t. It just generate the in the beach this scene, and there is a conditional score. The conditions is based on the alien, that okay, if you have the what is the score for the alien. Now if you have to combine those two score, like the alien score of the alien and the score of the in the beach, the generic idea is to, when you are doing the denoising at each step, you start with the unconditional score and you guide toward the conditional score. So basically this is like how those scores are combined. So you can see the main motivation is you start with the unconditional score and guide towards the conditional score. So it has been observed that the way of guiding actually guide the diffusion trajectory towards the text condition, and it generate the quality, like better quality image. For example, here you can see that the unconditional score shows a beach, but the conditional score shows a alien. When you combine those, it shows alien in the beach. That's our goal. And since these scores are generated during the denoising process, this does not require any kind of training. You can just combine the score in this way, and will generate better quality images in the inference step. So we motivate from this idea, and we thought, can we explicitly do something to improve the quality? Because here the goal is to guide towards the text condition, but not to generate the good quality per se. So yeah, in this context, we propose the perceptual guidance strategy. The idea is similar, but a bit different, which I'm going to explain. What we start with a lower quality image and we guide toward a better quality image. So therefore, our goal is to explicitly generate good quality image instead of aligning to the text condition, which was the goal for classifier free guidance. Now, therefore, suppose if you have to generate a good quality image of this identity. So you start with the bad quality score, and with the bad quality score, we generate from the model, which is not trained with the perceptual loss, like here for the kurtosis loss, what we mentioned. And suppose there is another score which is generated through the perceptual quality loss, like kurtosis concentration loss. Now we combine those two scores in this way that it start with the unconditional score and guide toward a better quality score. Similar way what classifier fee guidance did that. And here we combine like these two images to generate even better quality images. So for example, you can see that it start with this bad version of the image, and it's try to guide toward the better quality version of the image, which is generated using this theta p. And finally, when you combine those two, it generate even a better version of this image, which we get through the perceptual loss. Yeah. Okay. So this is the perceptual guidance strategy which we proposed. And so as I mentioned, that the design advantage of the classifier guidance, which was already there, was that its goal is to guide toward the text condition, but it can't be applied to any unconditional model because it actually depends on the condition. Compared to that, the perceptual guidance strategy is the goal is to guide toward better quality images, and it can be applied to any kind of unconditional like models. And additionally, it is a complementary to classifier fee guidance. For example, you can add classifier fee guidance. On top of that, you can also add perceptual guidance that will generate the even better quality image. Yeah. Now I'm going to the qualitative results. For example, here you can see the task we address is super resolution, where your input would be a degraded version of the image, and your goal is to generate a better quality version from the degraded images. Here you can see when we add the kurtosis loss, when we like there is a baseline guided diffusion. You can see when you do this super resolution, the eye quality is kind of getting a bit hazy. But when you add the kurtosis loss, the eye quality is getting better. And when you use the perceptual guidance strategy, the eye quality get even better. So that is a one kind of example where how it actually generates better quality images. And our observation or our hypothesis is that this kurtosis loss is doing some kind of locality specific smoothing. For example, when we generate this super resolution image, there are some irregularity in the eye region. So, but kurtosis loss understand uh, where the inconsistencies are and try to improve upon doing some kind of locality based smoothing to improve the quality even further. So here are some quantitative results for the image super resolution task. We verify this on guided diffusion and latent diffusion model with respect to image quality and image diversity. And we just use like a standard metric, FID score, PSNR, SSIM, music score. And to identify image diversity, we measure the LPIP's diversity, and shows that when we add the kurtosis loss or the perceptual guidance strategy, the quality improves across benchmark and across methods. We also validate this for multiple other tasks like unconditional image generation, personalized few shot fine-tuning tasks like Dream Booth. And here are some perceptual evaluation that we notice that we try to understand how the kurtosis loss or perceptual guidance strategy is improving the image quality. To identify that, we also measure the perceptual artifact ratio during the generation process for guided diffusion or latent diffusion model. And we have noticed that when we add the kurtosis loss, which is a naturalness loss, the perceptual artifacts are also reduced, both qualitatively and quantitatively. So for qualitative results, we have shown some example where you can see the without the kurtosis loss, there would be some perceptual artifacts which is got smoothed out when we add the kurtosis loss, which also makes sure that this loss a naturalness preserving loss. And we also quantify this across the phase data set across different setting, and we find out without the kurtosis loss, with the kurtosis loss, the number of the overall perceptual artifact ratio reduces. So that's how it's making the generation more naturalistic. But these metrics are might always not reliable. That's why we also did human studies using Amazon mechanical turkers, and we find out the kurtosis loss is performing better compared to the baselines in through human ratings as well. So yeah, so these are the work, and yeah, after there are some future work in this direction. So when we generate using these images, we can also use some kind of generation with reasoning or 3D or video generation, and also maybe combining diffusion and LLMs to generate using reasoning. So these are the future directions. Thank you, and I'm happy to take any questions.